This cube is special. It is computed and rendered on the GPU. Let me show you how it's done. We are going to work with DirectX 11, which means we should first do some setup. This step is very similar for all the graphics APIs you would use, but there are specifics, of course, also depending on your operating system. In Windows, I first need to create a window. We start by filling out the structure called WND class X. Think of it as a blueprint. It tells Windows the basic personality of our application, like what icon to show in the taskbar, what the mouse cursor should look like when it hovers over it, and the internal name of this class, which we call DX11 Cube Window class. We then hand this blueprint over to the operating system using register class X. Once Windows has our blueprint on file, we can actually order the construction. We define a rectangle to set our canvas size, which I have hard-coded to a classic 800 by 600 pixels. Then we call the createWindow function. We pass it our blueprint name, a title for the top bar, and tell it to use a standard overlapped window style, so we get the normal minimize, maximize, and close buttons. At this exact moment in the code, the window exists in the computer's memory, but it is completely invisible. So the very last step is calling show window. This pops the blank canvas onto our monitor. Right now it is completely empty and knows absolutely nothing about 3D graphics or the GPU. It is just a hollow Win32 shell waiting for instructions. But without this crucial first step, DirectX would have absolutely nowhere to display our final rendered pixels. Speaking about rendering, here is the secret that every graphics programmer eventually learns, but possibly the hard way. The math itself is not always the bottleneck. The real bottleneck is the shipping department. Getting our 3D data, our vertices, textures, our rotation matrices, out of the CPU's memory, across the motherboard and into the GPU's memory is incredibly slow compared to how fast the GPU can actually process it. Our entire goal with DirectX 11, and the reason our code might look a little intimidating at first glance, as you will see in a moment, is all about the logistics. We want to package our data as efficiently as possible, send it to the GPU in one big truckload, and then tell the factory workers, okay, you have everything you need. Now go paint the screen and don't let yourself be interrupted until you are completely done. So, now we know the GPU is a massive factory, but what exactly is the assembly line inside it? In graphics programming, we call this the rendering pipeline. It is a strict, step-by-step process that turns a bunch of mathematical coordinates into the 3D images you see on your screen. Think of the rendering pipeline like a car factory. You can't paint the car before you've built the chassis. The very first stop on our GPU assembly line is the input assembler. Its only job is to gather up all the raw materials we sent over from the CPU. In our code, there is a list of vertices, the 3D points in space that make up the corners of our cube. Once the input assembler has gathered the points, it hands them off to the Vertex shader. This is the first time we actually get to run our own custom code on the GPU. You can think of the Vertex shader as the cameraman. It takes those raw 3D coordinates and applies mathematical transformations to them. It calculates exactly where those points should be based on where our virtual camera is looking and how the cube is rotating in our 3D world. Next up is a fixed part of the GPU called the rasterizer. If the Vertex shader is the cameraman, the rasterizer is the draftsperson. It takes those newly positioned 3D points, connects the dots to form the triangles, and then squishes them completely flat onto a two-dimensional grid. It figures out exactly which pixels on your physical monitor are covered by those triangles. And finally, we reach the pixel shader, or fragment shader. For every single pixel that the rasterizer flagged on your screen, the pixel shader runs a tiny piece of custom code to ask one simple question. What color should this exact dot be? This is where we look up our textured image, map into the shape, and give our cube its final visual look. Once the pixel shader is done, coloring everything in, the frame is complete and it gets shipped off to your monitor. That entire process from the input assembler down to the pixel shader happens millions of times every single second. It is fair to say that the rendering pipeline can have way more stages depending on the API you are using and of course on the target hardware. Take what we just discussed as a baseline, sort of the smallest common denominator, which can be, and frequently is, expanded. Back into action. When our empty Windows canvas is sitting on the screen, it is time to wake up the graphics card. We start by setting up a structure called DXGI, Swap Chain Descriptor. DXGI stands for DirectX Graphics Infrastructure. It is the low-level bridge between your graphics hardware, your monitor, and DirectX itself. Inside this swap chain description, we are setting our frame rate to 60, choosing a standard 32-bit color format, and telling it we want one big buffer to draw on. Once that blueprint is ready, we call the most important initialization function in the entire API, D3D11 create device and swap chain. This single function gives us the three holy grails of the DirectX programming. First, the swap chain, which we use to flip our rendered frames to the monitor. Second, the Direct3D device. You can think of the device as the factory manager and the wallet. Anytime you need to allocate memory on the GPU, like creating a vertex buffer, loading a texture, compiling shader, you ask the device to do it. It owns all the resources. Third, it gives us the device context, specifically the immediate context. If the device is the manager, the context is the foreman on the factory floor. It doesn't create memory. Instead, it issues the actual commands. When you want to clear the screen, bind the buffer to the rendering pipeline, or tell the GPU to actually draw out triangles, you give those orders directly to the context. But before we can draw anything, the GPU needs to know exactly where in the memory it is allowed to paint. Just having a swap chain is not enough. We have to extract the hidden back buffer from the swap chain and create what is called a render target view. A view in DirectX is basically a mathematical lens that tells the GPU how to look at and interact with a chunk of raw memory. We created this render target view so the GPU can write colors to it. But we also need one more view, the depth stencil view. Our cube is fully 3D, which means as it rotates, some sides will move behind other sides. The depth stencil is a special invisible texture that keeps track of the physical distance of every single pixel from the camera. If the GPU tries to draw a pixel belonging to the back of the cube, the depth stencil checks the math and says, no, there is already a front-face pixel closer to the camera right there. Without this depth buffer, our cube would look like a bizarre inside-out optical illusion, where back faces override front faces. We saw it in the previous video. Finally, we define a viewport, which simply tells the rasterizer the exact physical pixel dimensions of our window, tying the mathematical 3D space strictly to our 800 by 600 screen. With all these views and context logged in, our Direct3D foundation is officially primed, connected to the operating system, and ready for our 3D data. So let's send some raw materials to our GPU factory. We have a struct here called simple vertex. This is the fundamental building block of our 3D world. Inside the struct, we aren't just storing the 3D position of a corner, the pos variable. We are also storing its texture coordinates, the text variable, which tells the GPU exactly how to pin our image into the shape. I have a video dedicated to texture mapping if you want to learn more. To draw our cube, we create an array of these vertices. But if you look closely at the common code you might see for this use case, specifically the indices array right below it, you might wonder why we need two separate lists to draw one object. Think about a standard cube. Each corner is shared by three different flat faces. If we just send a massive list of every single triangle to the graphics card, we would be sending the exact same corner coordinates over and over again. Memory on the GPU is precious, and sending redundant data across the motherboard is the ultimate performance killer. So instead, we use a vertex buffer and an index buffer. The vertex buffer, which is our vertices array in the code, is just the master list of the unique points in space. The index buffer, that's the connect the dots instruction manual. It tells the GPU, hey, to draw the front face, grab vertex 0, vertex 1, and vertex 2 from the other list. This setup saves a massive amount of memory and bandwidth. But what about things that change every single frame? Our cube is spinning, and in a real game, our camera would be moving. We cannot bake that dynamic movement into a static vertex buffer. That is exactly where our constant buffer comes in. Here you see updating the mWorld, mView, and mProjection matrices, which lives inside the constant buffer. We ship this tiny package of math over to the GPU every single frame. It acts as a set of global variables that our shaders can read from, allowing them to figure out exactly how to rotate and project our cube onto your 2D screen at the exact millisecond. We have successfully shipped our vertices and matrices over to the factory floor. It is time to give the workers their actual instructions. Here you see a massive block of text stored inside a shader source string. This is not C++. This is HLSL, the high-level shading language. It is a mini program that gets compiled and sent directly to the GPU. Inside the string, we have two main functions: VS for the vertex shader and PS for the pixel shader. These are the absolute brains of the operation. Let me tell you immediately that there is a better way of organizing this. In a production, you most likely want to have the shader files saved separately, added to your project, living as independent entities. Now I opt for putting everything into one long C++ file, but it is for learning purposes only. I think it is easy to digest, easy to follow, even if you are not familiar with Visual Studio or any IDE really. So to keep it simple, easy to understand in principle, we have everything stacked here. In a professional setting, you will see dedicated shader files, so don't be surprised. Maybe one hint if you are using Visual Studio. If you want to solve all the dependencies, just add this NuGet package into your solution. Let's look at the vertex shader first. Every single vertex we put into our buffer gets passed through this function, one by one. Do you see these three multiplication lines where we take the input position and multiply it by the world, view, and projection matrices? That right there is the fundamental math of 3D graphics. Again, I have a video just about that. Playlist with everything graphics related will be down in the description. The world matrix moves, rotates, and scales our raw cube into its proper place in the 3D scene. The view matrix represents our virtual camera, essentially moving the entire 3D world around the lens to simulate looking from a specific angle. Finally, the projection matrix does the heavy lifting of squishing that 3D scene down into a flat two-dimensional image, complete with field of view and perspective, so things further away look realistically smaller. By the end of those three lines of code, our 3D corner has been successfully mapped to a specific 2D coordinate on your physical monitor. Once the GPU has connected those projected dots into flat triangles, it hands the job over to the pixel shader. Remember, the pixel shader runs for every single pixel that makes up the surface of our cube on the screen. It is usually the most performance-heavy part of any modern video game. But our pixel shader is incredibly simple. It takes the UV texture coordinates that survive the journey from our C++ tract, and it uses a built-in function called sample. This tells the GPU to look up the exact color of our loaded image file at a specific coordinate. It returns that color, and boom, we have a fully textured, mathematically accurate 3D object. We can also do this to have just one colored cube, but it would look weird as we don't have any lighting. Maybe next time. To have a complete picture and mental model, let me summarize. How do we actually wrap our image around all of this math? If we look at the simple vertex struct again, we have a text variable which holds an x and y coordinate ranging from 0 to 1. This is called UV mapping. It tells the GPU exactly how to stretch our image, which is the DX JPEG, across our flat triangles. We load that image down in the initDevice function using createWIC texture from file. And right below that, we create a sampler state. The sampler is basically a set of rules. It tells the GPU what to do if the virtual camera gets extremely close to the cube, or very far away, usually applying filters so the image doesn't look like a pixelated blocky mess. Finally, we bring everything together in the render function. This is the heartbeat of our application. This function runs every single frame. First, we calculate exactly how much time has passed using getTickCount64. We use that to update our rotation math. Then we have to do some vital housekeeping. We call clearRenderTargetView to paint the entire screen a dark gray, wiping away the old frame completely. We also create the depth stencil view, which is the mathematical trick that ensures the front of the cube actually blocks the back of the cube from being drawn. Next, we send our freshly updated rotation matrices over to the GPU using update subresource. Then comes the final roll call. We bind our vertex buffer, our index buffer, our compiled shaders, and our texture directly to the immediate context. We are explicitly handing the factory workers their tools for the specific job. Once absolutely everything is in the proper place, we issue the command drawIndex. We tell the GPU to draw 36 points, representing the 12 flat triangles that makes up our 6-sided box. And the very last line of the function is present. This is the swap chain action we talked about earlier. We tell the graphics card that the back buffer is finished and it is time to instantly swap it to the front so the user can see it. The monitor updates, the function ends, and the loop starts all over again for the next frame. It might seem like a massive amount of code just to spin a texture box, but you have just built the exact same foundation that powers modern high-end game engines. If you want to learn more about the concepts mentioned here, there is a whole playlist of computer graphics topics in the description, but here let me put this into your attention. If you found shaders interesting, check out this video where we play with mesmerizing mathematical structures. Thanks for watching. If you want to see more in the future, don't forget to click the subscribe button, and ciao!